Okay, great. So now I want to go on, and as the title of the lecture suggested, talk about constraint satisfaction problems more generally. In some sense, max-cut, which we've been focused on for a while, is almost like the simplest constraint satisfaction problem. So now I want to talk about them more generally and about approximation algorithms for them more generally. And I'll start calling them CSPs. That stands for constraint satisfaction problems. Okay, so constraint satisfaction problems are a pretty wide class of algorithmic problems or tasks. And many well-known algorithms problems are examples of constraint satisfaction problems. So the max-cut problem is a constraint satisfaction problem, and the 2-sat problem, and the 3-sat problem, and the k-sat problem are CSPs. Trying to 3-color a graph is a CSP. Trying to solve a system of linear equations is a CSP. Not every problem is a CSP, but a lot of cool problems are CSPs. So in order to say, instead of just directly diving into the definition of CSP, which is a little bit elaborate, let me talk about 2-sat specifically for a moment and why it's a CSP. It'll help us learn some of the terminology. So remember the 2-sat problem. I'm sure you've heard of it before. The input looks like this. It's like a 2CNF formula of a bunch of variables, x1 through xn, and a bunch of clauses, each of which is like the OR of 2 literals. And you're trying to find a truth assignment that, ideally satisfies all of these clauses. So what are some of the ingredients of this 2-sat problem, or the input? Well, first of all, the one ingredient is the variables, x1 through xn. Another ingredient is what I like to call the domain. The domain is like the values that you're trying to associate to the variables. Okay, so sometimes in, the SAT problem, you call them 0 and 1. Sometimes you call them true and false. Let's just call them true and false for now. So in 2-sat, you're trying to assign true or false to every variable. And well, the other main ingredient in 2-sat is the clauses, which we're going to call constraints because we're going to start talking about CSPs. And each one is a constraint. It's because they're ANDed together. This clause is a constraint, like you want x1 and x3 to have a true OR, and you want this clause thought of as a constraint to be true of your assignment, and you want this clause to be true of your assignment. I should say, by the way, it's going to come up again, but there's an unfortunate behavior in algebra and constraint satisfaction problems in that people don't make a clear distinction between a variable and an assignment to a variable. But we're going to try to keep those two things very separate in our heads in today's lecture, the difference between a variable and an assignment to a variable. Okay, so in 2-sat, it would seem that you just say, okay, yeah, you can have any number of clauses or constraints, and each one should be the OR of 2 literals. But in order to define constraint satisfaction problems in general, I really don't want to talk about literals. If you recall, a literal is a variable or its negation, but I don't want to talk about negations. I just want to talk about variables. So in fact, I don't want to say that the constraints are ORs of 2 literals. I want to say it differently. So let me call, in my little example here, let me call the clauses or constraints, as I'll start to call them, C1, C2, C3, and so forth. So let's take a look at C1. C1 is nothing too funny. C1 is the OR function, or the OR predicate, or the OR constraint, or the OR relation. Those are all synonyms, applied to variables x1 and x3. Okay, what about C2? I want to claim that C2 is also some predicate or relation, or little function, applied to variables x2 and x4, but I don't want to mention literals. So does anybody know what predicate is being applied or is constraining x2 and x4 here? You can type it into the chat. All right, well, for those of you who just want to enjoy the show, it's NAND, right? This constraint is specifying that they can't both be true. x2 and x4 cannot both be true because that's when this clause fails, this OR fails. Yeah, very good. Somebody got it, NAND. There's just a little lag, I suppose, between when I ask and when people quickly type. Great, so what about C3? C3 is another clause that's somehow constraining x2 and x11. What variable or what predicate is constraining x2 and x11 here? Check in the chat. I guess it's like some implication or something, like maybe implies or something, but I don't want to stop talking about it this way. Let me just call it this. It's like the OR function, except you negate the first input. Okay, that's what's going on here. In other words, it's the the predicate with this truth table. Yeah, I suppose that's commonly called like implies, but yeah, very good. Somebody said it on the chat. But yeah, I think what's best is to think about it is like actually in 2SAT, there's like 4 kinds of constraints you might have. Each one is sort of like the OR constraint on 2 variables, except that you're allowed to have negations on inputs. Okay, so instead of making a literal into a first-class object, I just want the variables to be first-class object and talk about changing the constraints. So in the 2SAT problem, you don't have like one kind of constraint, like OR of 2 variables or literals. I want to say that you have a set of 4 allowed constraints, OR, but with the second input negated, OR, but with the first input negated, and OR, but with both inputs negated. And each of these 4 constraints has what I'll call arity to. Arity means just the number of variables to which the constraint applies. And actually, to be super technically correct here, the CSP I'm describing is usually not called 2SAT. It's usually called E2SAT. This E referring to the fact that every constraint involves exactly 2 literals. It's a very minor point. Well, it's not so minor, but it's a technical point. Usually when people just say 2SAT, they allow clauses of length up to 2. But for now, we're describing, the version where every clause has to have exactly 2 constraints. So instead of writing the input like this, is like, first of all, I'm not going to write it as a conjunction. I'm just going to write it as a list of constraints that I want to be true. And yeah, each of these constraints, I'm going to say, okay, it's one of the predicates or constraint types from my set applied to, in this case, 2 of the variables. Okay, and these pairs of variables are called the scopes. Like in this first constraint, the OR with no negations is the predicate, and the pair x1, x3 is the scope of this predicate. And again, just as this minor point, in the formal definition of CSPs, the scopes are required to involve distinct variables, which is why this really only lets you have it's like E2SAT, you're only allowed to have ORs of 2 distinct literals. You can't do this trick of like, oh, if you want to just have the constraint x1, I'll just do OR of x1 and x1, because I want the scopes to be distinct variables. Okay, so in light of that, if you want to capture just plain 2SAT, where you're allowed to also have clauses of length 1 and literals of length 1, then you have to add 2 more predicates of arity 1, which you could call OR and sub 1 and OR sub 1 with negation. Or like, I guess it's like the identity function on one variable and the negation function on one variable. Okay. So let me give the formal definition now, and this is like it's like a sort of annoyingly complicated definition. So if you have any questions, definitely type them into the chat. So in general, a CSP is defined by a couple of things. First of all, the domain, which I'm going to call omega, and remember, this is like the values you want to assign to the variables. So this domain was true and false for 2SAT or SAT-like things, but like for 3 coloring, the domain is going to be like red, green, blue. And it's most often just like the integers from 0 up to some q minus 1, and often q is 2. So it's like often you're concerned about like binary constraint satisfaction, sorry, I should say Boolean constraint satisfaction problems, where you're trying to assign like 0 and 1 to every variable. But the main thing that defines a CSP is the set of predicates that are allowed, sort of the set of constraint types that are allowed. And I'll call this capital psi. And this set can have 1 or more predicates in it. Like for E2SAT, it had 4 predicates. And every little psi in this set is a mapping from like an R tuple of domain elements to 0 and 1. And here 0 and 1 means satisfied and unsatisfied. Okay, and R is the arity of the constraint. So remember, like for the 2-sat or E2-sat CSP, omega was true and false. All the arities were 2. So our constraints, little psi, we're supposed to map a pair of true-false values to 0 and 1, meaning satisfied or not satisfied. And indeed, like, you know, the first one of the 4 constraints was the OR function, which maps a pair of truth values to 1, unless both those truth values are false. And you can have different arity, your psi's and your big predicate set can have different arities if you want. Like if we wanted to capture 2-sat, remember we needed some OR type predicates of arity 2 and 2 OR type predicates of arity 1. That's fine. And that's it. So once you define the domain, and most especially the set of predicates, that defines a particular kind of CSP, like, as we'll see, max cut or 3 coloring. So that's like the problem, but now you have like an input or an instance of the problem. The input or an instance of a constraint satisfaction problem is, well, it's like a set of n variables, which we'll just call V, together with a list of constraints. And the list of constraints is the main thing. And think of like the clauses in our 2-sat instances. Each constraint C is a pair. I usually write the other way, psi S. I'm not sure why I wrote S psi here. Anyway, psi is one of the predicates from the set. It'll have some arity R, and S is the scope. And the scope, remember, is a tuple of distinct variables, and there should be R of them for a predicate of arity R. Okay. Good. So that's all the terminology involved in a CSP. And my computer is really chugging. It freezes at the start of each new slide. Okay. So let's see some examples. So one, I said, you know, one of the simplest possible examples is max cut, and that's true. So max cut, well, on one hand, sometimes we describe it, oh, you're given a graph and you want to partition the vertices into 2 parts to cut as many edges as possible. But you can really think of that as a CSP as well, where the vertices of the graph correspond to variables, and the edge of the graph corresponds to constraints. So it's like a funny way to write a CSP. So there, the domain, I should say plus or minus 1. It's a little bit of a funny typo. The domain is plus or minus 1. If you imagine you want to assign, let's say, +1 and -1 to each vertex. And the predicate set only has one predicate, and that predicate is the not equals predicate, which maps a pair of plus or minus 1 values to, you know, satisfied or unsatisfied. Okay, it's really like capturing max cut, right? You want to assign 2 values to each of the vertices, and you want to, every edge is saying like, please cut me. It's like saying, please assign my vertices not equals satisfying values. Okay. What about 3-sat? So 3-sat is one of my favorite CSPs. It's classic. And you can call this domain true false if you want, but let me switch now to maybe the more standard computer sciencey way of describing it, where the domain is 0, 1. So you're trying to assign 0, 1 values to all the variables. And remember, you know, now to accurately capture 3-sat, you need like a lot of constraint types. You need all, because you're not allowing literals, you have to build it into the constraints. So you're allowing you can OR together 3 variables, or you can OR together 3 variables, but like put a negation on the 3rd one. And there's like 8 ways to do this, ending with you can OR together 3 variables while negating all the variables. And then there's all the, because in 3-sat you usually allow clauses of size 2 and 1, so there's all the 4 OR type functions of arity 2, and there's all the 2 type OR functions of arity 1. Okay, so 3-sat, when you write it as a CSP in this way, like the predicate set, capital psi, has 14 predicates in it. On the other hand, if you care about E3-sat, that again just refers to all the clauses having to have length at exactly 3, and so then psi would just have the 8 arity 3 kind of ORs. This is a pretty cool constraint satisfaction problem is called NAE3SAT. And there again, it's kind of like 3SAT. The domain is 0 and 1. And psi is also going to have like 8 constraints, but I'll just say it's like you take the NAE3 predicate, plus you allow literals. And what is NAE? It stands for not all equal. So the not all equals predicate is satisfied if, well, the truth values x, y, and z are not all equal. So it's unsatisfied if they're all equal and 1 otherwise. Okay, so it's kind of like a weakening of 3SAT. Like in 3SAT, you know, an OR is satisfied if you get at least one of the literals to be true. And not all equals 3SAT, you want at least one literal to be true and at least one literal to be false. Maybe I guess it's a strengthening of 3SAT. Anyway. 3 coloring is a very popular algorithms problem, and it's also a CSP. So here the domain, again, it's like a, you think of it on one hand as like a graph. You're trying to color the vertices with 3 colors. But again, you know, you can think of the vertices as variables, and the domain is like red, green, blue. So you're trying to assign one of 3 colors to each vertex. And each edge is just insisting that its endpoints get not equals colors again. So here again, the predicate set only has one predicate. It's the not equals predicate. Although formally, this is not equals predicate that takes a pair of colors and outputs whether or not they're unequal. Let me tell you one more CSP. There are plenty of others. I'll tell you one more. This is not quite a standard name, but I'll call it bijection parentheses q. So in this CSP, the domain is just a set of size q. You can call it 0 through q minus 1. And what predicates are allowed? You actually allow a lot of predicates. They're all binary predicates. So they take 2 values, let's call them A and B. And any psi is allowed so long as it has what's called the bijective property. And that means it should be that for every little a that you plug in for the first value for psi, there should be a unique b that makes psi satisfied. Okay, so for example, max cut has this property because with the not equals constraint, you know, over a plus or minus 1 domain, like no matter what you assign for like a first vertex, there's exactly one way to assign the other vertex to satisfy the constraint. Okay, but it doesn't have this property in 3 coloring, right? Because, you know, if you assign one vertex red, there isn't a unique, you know, correct way to assign the other one. You can do green or blue. But max cut is an example with this property, or if you have like a constraint that's like an equation, xi minus xj equals 7 mod q. This is also a bijection constraint. Xi minus xj equals 7 mod q, because for every assignment to xi, there'll be a unique value assignment for xj that will differ from it by 7 mod q. And this CSP's real name, or most usual name, is this weird name, unique games. Okay, and it's related to this unique games conjecture you might have heard about, and which I'll talk about at the end of this lecture, briefly. Okay, so this is a bunch of CSPs. And, okay, what are you trying to do with the CSP? Right, so given an instance I, this is my weird capital cursive I, you're trying to come up with an assignment. What is an assignment? It's a map F that assigns to each variable a domain value. Okay, and we say that a constraint C, psi comma S, is satisfied if, you know, when you assign the variables in its scope according to F, you know, the constraint outputs 1. Okay, so F of S is my shorthand just for F applied to each of the variables in the scope S. Further definition, we say the value of F is, I'm going to call it not the number of satisfied constraints, but I prefer to call it the fraction of satisfied constraints. Pretty much the same difference. So this will always be, I do that because I want the value of an assignment to always be between 0 and 1. And so like a funny way to write it would be you average over all the constraints of just the predicate applied to the scope with this assignment F. And that works because I have my predicates outputting 0 or 1 for whether or not they're satisfied. Okay, so then if you just average all these 0, 1 values, you indeed get the fraction of satisfied constraints. And finally, I'll say the optimum of the CSP, denoted opt of I, is, well, it's a natural thing. It's the maximum possible value you can achieve over all assignments F. Okay, so you're trying to find the assignment which maximizes the fraction of constraints that it satisfies. Okay, so like in maxcut, right, you're trying to find a partition that maximizes the number of constraint or edges that you cut. And you can even think of things like 3SAT as like a sort of optimization problem where you're given a 3 CNF instance. You know, one thing you might think about is just whether or not there's an assignment that satisfies all the clauses, but more generally, you could try to find an assignment that satisfies as many clauses as possible. Okay, and we say that an instance is satisfiable if its optimum is 1, meaning there's an assignment satisfying 100% of the clauses or constraints. Okay, so I'm going to talk about 3 algorithmic tasks associated with CSPs. So one task given a CSP is the satisfiability task. And that's a simple task. You're given the instance, and you just want to decide if it's satisfiable, if the optimum value is 1. This is like the classic task associated with like the 3SAT problem. You're given an instance, you know, is there an assignment that satisfies 100% of the clauses / constraints? And, you know, you might also ask, you know, if you find out that it's satisfiable, you might want to find a satisfying assignment. But actually, if you can efficiently decide if a CSP is satisfiable, then you can also efficiently find satisfying assignments for it. And that's by a self-reduction trick. You know, you just try setting the first variable to some domain value and ask yourself again, hey, is it satisfiable? If so, great, freeze that assignment. If not, try the next assignment. And you can go through all the variables like iteratively and find an assignment that preserves the fact that the CSP is satisfiable. And if you're, you know, don't mind about polynomial time, then this reduces the problem of finding a satisfying assignment to just deciding whether or not an instance is satisfiable. Okay, the second task associated with CSP that I want to talk about is optimization. And, you know, nothing in this life is perfect, so maybe you run a satisfiability algorithm or you try to, and you find it's not satisfiable. We still might want to try to find the assignment F whose value is as large as possible. Ideally, whose value is equal to the optimum value. That's optimization. And now this third one is maybe the kind of task you thought about least, but it's equally important. I call it certification. And it's this task. Given an instance I, output a number beta, which is as small as possible, but you have to be guaranteeing that you're outputting an upper bound on the optimum. So like an algorithm here is going to output like a number like 0.9 together with like an ironclad guarantee that like I analyze this instance and I'm confident the optimum is at most, you know, 0.9, 90% of the constraints. Even more ideally, it would be for you to output like some kind of like vivid certificate that the optimum is at most beta. But as long as you like output a number that's like 100% guaranteed to be correct, then we call you a certification algorithm. Okay, and of course your goal is to output a beta that's as small as possible, ideally one that's equal to the optimum value. Okay, so let's talk about each of these 3 tasks in turn, because there's interesting things to say about each of them. So let's start out with CSP satisfiability. So perhaps the most interesting question to ask here is, what's going on with, you know, the satisfiability task? Because sometimes, for some CSPs, you can do it in polynomial time, and for some CSPs, it's NP complete. And like, what's the deal? So for example, the satisfiability problem for maxcut, I claim, is in P. Why is that? Well, in the satisfiability version, you're not sort of trying to find the optimal cut. You're just trying to ask, is there a partition that cuts 100% of the edges? And that's exactly equal to deciding, or equivalent to deciding, if the graph is bipartite. It means there's a partition of the vertices into 2 parts, such that all the edges go between the 2 parts. And as you imagine, you know, there's a simple polynomial time algorithm for that. And I'll even say what it is in just a moment. On the other hand, like 3SAT, you know, it's the most famous NP complete problem. I give you a 3 CNF, I ask if it's satisfiable or not, that's NP complete. Okay, this not all equals 3SAT problem is also NP complete. 3 coloring problem is NP complete. So sometimes CSP satisfiability is NP complete, but sometimes it's in P. So in fact, this like bijection problem I mentioned is in P. And well, deciding if an instance is satisfiable is in P. And the reason is basically some kind of propagation algorithm. This actually includes an algorithm for max cut, because max cut is a special case of this bijection problem. Why? Well, you can just take any vertex in a bijection instance and try all the possible assignments for it. And for each one, like assuming this variable participates in some constraints, the bijection property of the constraints means as soon as you decide on a domain value for one variable, all the constraints, by the way, are binary. It forces a unique choice for all of the assignments, the variables that it participates with in constraints. So it like forces some other values if you're going to be fully satisfiable, and those in turn force some other variable assignments if in turn you're going to be satisfiable. And you can just propagate this and check if you ever get like an inconsistency. It's like breadth first search. And as long as you do that for like each connected component of the constraint graph, and as long as you like try every possible assignment for one of the vertices or one of the variables in each component, then you can decide efficiently whether or not such an instance is satisfiable in polynomial time. Okay, so yeah, so how can we tell the difference? So for example, 2-sat, NP or NP complete? Well, this is definitely non-trivial, but you probably know that it's in P, actually. You can decide if a 2CNF instance is satisfiable or not. 3lin mod 2. This is a CSP where you have like linear equations. Each linear equation involves 3 variables, and it looks like this, but everything is happening mod 2. This is a CSP. All the constraints have arity 3. The domain size is 2. This CSP is in P, because it amounts to solving a system of linear equations over a field to determine if it's completely satisfiable or not. What about 1 out of 3 sat, where, you know, in each clause, instead of trying to get at least one literal true, you're trying to get exactly one literal true? NP or NP complete? Turns out it's NP complete. What about this CSP called order 10? This is the problem where every variable can be assigned a value between 1 and 10. There's only one constraint type. It's the less than constraint. So you have a bunch of, you can think of it like as vertices, and you have a bunch of edges, directed edges. And the directed edge implies that, like, you know, this head of the directed edge should be less than the tail of the directed edge. And you have to assign a value 1 through 10 to each vertex. Can you check if this is satisfiable or not? This is also in P. You have to think about why, but you eventually take this instance and do a topological sort of the graph and see if it has depth at most 10. Okay, so you can see that, like, there's lots of different kinds of CSPs, and sometimes their satisfiability problem is in P, and sometimes it's NP complete, and like, what's the deal? So let me tell you a little story about this situation. So in 1993, Feder and Vardy were thinking about this, and they made a conjecture, and they made the following conjecture. They conjectured that every CSP satisfiability problem is either in P or NP complete. And, you know, it sounds funny because I didn't really mention like a third possibility before, but there are third possibilities. You may know this theorem in complexity theory called Ladner's theorem, which says that assuming P does not equal NP, there exist NP intermediate problems, problems which are neither in P nor are they NP complete. Well, the Feder-Vardy conjecture says this does not happen for CSPs. Every CSP they conjecture is either in P or NP complete. So there's like the easy ones or the hard ones. And this became known as the dichotomy conjecture. And much later, 12 years later, Bulatov, Jevons, and Krokhin, who had thought about it, well, many people had thought about it for some time, they proposed a strengthening of it called the Algebraic Dichotomy Conjecture, which basically told you which CSPs should be in P and which ones should be NP complete. Like, they gave you a rule. And this rule was very sophisticated. It was an algebraic rule using ideas from an area called universal algebra. But they basically gave you some, like, you know, abstruse algebraic condition such that if it was satisfied, they conjectured that this CSP satisfiability problem is in P. And if it's not satisfied, they conjecture that it's NP complete. And actually, strangely, this part of the conjecture was the easy part that was like known for sure. If, you know, your CSP doesn't have this problem, it was provably NP complete. What was missing was the hard part. is that these CSPs that do have this property are in P. So it's kind of a strange situation where people were conjecturing certain problems, those that satisfied this condition, had a polynomial time algorithm, even though they didn't know one. It's almost always just the opposite in complexity theory and algorithms, right? If you have like some problem and you can't figure out a polynomial time algorithm for it, you're like, well, probably it's NP complete. But here, they're like, we believe these CSP satisfiability problems are in P, although we don't know how to prove it. So there's lots of work on this conjecture. And let's see, it was proven when the domain size is 2, back in 1978, actually before it was even conjectured, by Schaefer. I think there's 2 F's in Schaefer. This is maybe a typo. So he proved that every Boolean CSP is in P or NP complete. And then in 2006, it was proven for CSPs where the domain is of size 3. And then in 2017, Bulatov and independently Zhuk proved it. So fantastic. So the dichotomy conjecture, and in fact, the algebraic dichotomy conjecture is a theorem. It's true. Every CSP is in P or it's NP complete. And this weird algebraic condition tells you, given a CSP, which one it is. Interestingly enough, the meta problem, given a predicate set psi, does it satisfy this algebra condition or not that makes you in P? That meta problem is NP hard, I believe. But, well, anyway. Good, so that's all I want to say about CSP satisfiability, but it's an extremely interesting area.